Hi, everyone. Welcome to this talk about AMD Quark. Quark is a broad model optimization framework that is being developed by my team at AMD for optimizing models for deployment, ONNX and PyTorch models. So this is our first talk since we open sourced Quark, which was approximately 2 months ago. And so today we'll take a few minutes to introduce you to Quark. Quite a lot has been said about model deployment already, so I'm going to go through some of the slides very quickly. And I think the content was fantastic. Some very key points were covered. But I do want to take a few minutes to talk about why we developed Quark. And then we'll go a little bit deeper into its capabilities. So in general, model optimization, whether it's for large inference systems in data centers, GPU-based systems, or on the client side, something like AI PCs, it's a complex process. And so Quark has been designed as a framework for end-to-end model optimization, primarily focusing on quantization, but there are other techniques in there as well. And in this talk, for context, I'll start with a few words on the problem of model deployment and how that relates to techniques like quantization. And then we'll talk a little bit about Quark's features in some depth. And finally, we'll get into a little bit more depth with a couple of, there are several flows in Quark. We'll focus on ONNX-based flows. All right, so when we talk about model optimization for serving, there are typically the engineer or engineers who are sitting in front of that system. They typically have high-level goals like throughput and latency. And throughput is typically for serving scenarios, it's queries per second. And latency. So these are common high-level metrics. Now, latency, improving latency improves the responsiveness of your applications. Having higher throughput reduces the total cost of inference for your inference system. So TCO gets down, which is kind of like what's really kind of the requirement these days. It's a race to the bottom. How can you reduce the cost of your inference? Just now, we were hearing that it takes more dollars to run inference for ChatGPT than it ever took for training ChatGPT or even continuously training ChatGPT. In practice, however, the metric that is most commonly optimized is a combination of both, throughput, but with latency constraints. Sometimes this is also called, recently, there's a term called goodput, where it's still throughput, but you discount queries that don't meet your SLA for latency. So, and that makes the problem of model deployment a little bit more complex. Latency and throughput typically have trade-offs, and there are different optimizations that are needed for both. And so with throughput, with latency constraints, it's a little bit more complicated. The batch size is no longer fixed, so the optimization problem becomes a little bit more complex. In reality, deployment of a model or a model workload on any hardware is a multidimensional problem, so let's peel one more layer off. I'll go through this very quickly. I think we are mostly familiar, but there's an interplay of several factors. So you have your workload to start with. It maps on these dimensions in a certain way. And then you have compute governed by the number of operations in your model workload. Memory required to load the model depends on the configuration. Working memory, this is a very tricky one. It's the memory you need for allocating buffers for your activations, KV cache. It is highly configuration dependent. You have paged attention in your software stack that changes the amount of working memory you need. And it's also kind of hard to estimate exactly how much working memory is needed. Power, we talk about this a little bit less. It's a very important component. Most of the hyperscalers, they don't care about just perf, but they measure things in perf per watt or perf per TCO, total cost of ownership or operation. And there are several devices where you can change the clock frequency, which changes the wall clock time for your inference, but at the expense of more or less power. Okay, and so you are given a source model, and then you have your system that you want to deploy it on. It is very common to see that the model workload exceeds the system capacity on multiple dimensions. In fact, with ever-increasing size of models, this is very, very common. And this is where model optimization techniques like quantization, pruning, they come in, because they give you these different levers how you can bring that model within the system capacity envelope. One thing to note is that accuracy thing, that is pretty much anchored where it is. You cannot change accuracy too much. Some of the social network hyperscalers estimate that you lose somewhere between $10 to $100 million per month for 0.1% drop in accuracy in some of their marquee models, like recommendation systems models. So that pretty much sets up the problem. The challenge, you have to optimize your model to fit within the system without sacrificing accuracy too much. Quantization comes in, gives you a lot of different levers. You go to a lower precision for computation and memory. Let's peel one more layer. I'm going to go past this slide real quick. OK, so here I wanted to quickly talk about peel another layer of what makes a quantization landscape a little bit complicated. Diversity of hardware backends is a big one. It's a major factor at AMD and all across. There is a lot of different hardware backends for AI workloads. These include data center CPUs like Instinct CPUs, EPYC CPUs, data center CPUs, and then Ryzen platforms, which is a combination of NPU and integrated GPU and other embedded SoCs. So each hardware backend has its own set of features, drives its own constraints and basically priorities. And so the quantization stack has to kind of respond to that, the driving of different requirements by different hardware backends. Composability, every hardware backend requires the optimization stack to compose with the execution software stack. And input-output model formats have to be aligned. Ecosystem, in general, you want to integrate very tightly with the downstream execution ecosystem. And so ONNX runtimes definitely there. PyTorch, you see, you need to be composable with Torch compile used for production deployment. And then there are other serving frameworks out there, VLLM, SGLang, Hugging Face transformers. So that's the composability angle. Use cases, every hardware deployment drives its own use case. And so, for example, are you just trying to shrink the memory requirement to fit a model like Llama 4 Maverick onto one, let's say, Instinct GPU, data center GPU? Or do you care about, you want to have maximal accuracy, in which case you want to do dynamic quantization of activations? Or if you want to have maximal perf, in which case you want to go do full ahead of time static quantization. Or maybe your model workload is just hovering at that threshold where it's just slightly above the working memory of your system. So you want to do something like KV cache quantization for LLMs to just bring it down enough to fit. So these are different use cases, and usually you have to mix and match. So your quantization framework should support these use cases seamlessly for rapid experimentation. Data types, I don't think I need to say too much about data types. 3 years ago, it was 16-bit types. 1 or 2 years ago, FP8, Int8 were the bleeding edge. Now they're talking about FP6 and FP4. And there's evidence that FP4 is all you might need for accurate inference. So, and imagine having like a BF16 kind of range compressed to something like MXFP4, where you have representable values between -6 and 6, multiplied by some scale factors, so few representable values. That requires advanced algorithms, advanced mathematics to do that, and you want the quantization toolkit to have several different options there so that you can try mix and match. And also there are a lot of variations within the data types. Finally, accuracy is king. You want to try different algorithms quickly. An interesting thing is, and I think a couple of speakers before me have alluded to this, which is that any optimization or any modification of your model requires a comprehensive evaluation. So the framework actually should have tooling that should allow you to evaluate the model rapidly. You're hearing that AI world is going through an evaluation crisis. Models are getting very, very big and very capable, so they're kind of pushing the envelope on evaluation. And that manifests itself in terms of like multiple metrics, multiple data sets. So the tooling here is, you'll be surprised at how much effort goes into just tooling to do that rapid experimentation and exploration. So all this makes the quantization landscape very complex. And At AMD, when we started looking at this quantization for multiple hardware backends, these were some of the problems we ran into. So we decided to have this one-stop shop framework for model optimization. And this is where AMD Quark became that horizontal layer across different hardware backends. And it has a complete set of features and tooling to support different use cases for different backends. Very quickly, I know I'm a little bit over time here, but and my colleagues Tiago and Boven will be getting into more detail here. But very quickly, these are some of the highlights of the Quark's capabilities. I'm not going to go through each one of them, just quick highlights. It supports ONNX, PyTorch models, Hugging Face, sub-formats. It's got a unified API. Support for a lot of different architectures, model architectures, a lot of different data types, algorithms, all the way from mid-tier algorithms to advanced algorithms like rotation algorithms. And ecosystem integration, I think this is a really good one. Quark is very tightly getting integrated with downstream ecosystems. ONNX runtime, obviously, but others like VLLM. I think there was a question in one of the things, how are things composing, maybe from Justin, how are things composing with downstream ecosystems other than ONNX runtime? So VLLM, SGLang, these are some serving frameworks which are really popular out there, so some of the integration with that. Production models, I think Quark is pretty much battle tested at this point. And so there are a lot of production workloads that are being shipped by customers, and it's used as the framework for some of these benchmarks like MLPerf benchmarks and Procyon. Finally, large model support. Quantization is a double inference problem. You need to run inference to quantize, calibrate the model, and then you need to run that for evaluation. And for both of them, typically, to get the baseline, you need to run the original full precision model, which could mean that you have to run this on multi-GPU. And so being able to quantize those Llama 405 billions and Maverick Llama 4 and all requires support for multi-GPUs, sometimes multi-node. So we have that support in Quark. Okay, I'm going to move on. I think Tiago will get into some more depth about some ONNX flows.
Hi all, my name is Tiago, and today I'm going to quickly talk about a little bit of the ONNX to ONNX flow in Quark. So we won't have time to go deep into the architecture itself, but there are some things that I would like to highlight for you guys. First, Quark does implement a post-training quantization flow. So that means that the users will have to provide, in addition to the full precision model and the quantization config that they want, also a data set that will be used in the calibration. So here in this diagram, we kind of see this PTQ flow going on. But they have like a kind of couple of tweaks for that Quark adds to it. So what else I can tell? Well, basically, we use the Q2Q pattern to do the quantization, which allow us to quantize this in CPU without having to worry about what is the hardware that we are going to quantize this to. That gives us that hardware agnostic kind of flexibility that we would like to have at AMD. Also, we are compatible with ONNX runtime 122.0 that was released a couple of weeks ago, I guess. And we use a lot of custom ops to test and experiment with novel data types. I think that Spandan mentioned MXFP, which we support. We also have block floating point and other types that we usually try on without having the actual hardware for it. In addition to that, in this flow, you can see that this block 2 and 5, it's not kind of a standard PTQ flow. So Quark kind of introduced these algorithms that, well, they're kind of self-descriptive, but these pre-quantization algorithms, they are not actually the quantization itself, but by transforming the models before the quantization, we can usually smooth those outliers that we see in our tensors. And by doing this smoothing, we usually have like better accuracy in our quantization. So popular pre-quantization algorithms that we support include Quark, SmoothQuant, cross-layer authentication, and others. What else? We do support these advanced algorithms, but I'm going to talk in a future slide, and we can see how it works better. No. Okay, so when we are doing quantization, one thing that we quickly learn is that's usually not like a one-shot kind of thing. So we do a quantization, we then run this evaluation step, and we can find out that that model is actually hard to quantize. Accuracy is pretty low, and we have to try again. And sometimes, again and again and again, until we do find that optimal set of parameters that do compress the model, but still preserves the accuracy that we need in production. So to help like automating this process, what we do is introduce this feature called auto search, in which the user can define what are all the quantization parameters that are kind of negotiable. All those parameters that you wanted to explore new range and new values to see if we can find that model that we'll be able to deploy. So it's kind of a dictionary-based kind of thing. You say, calibration method, I'm okay with entropy, min-max, or other parameters. You can say activation type, I will take int 8, int 16, whatever works. And Quark will then search across this search space, eliminate those that are invalid, and will evaluate each model that you get, rank them, and then return the ones that are better suited for deployment. Another feature that I would like to highlight is the mixed precision. So usually, traditionally, we would like quantize a model using a single data type across the board. With this comes a lot of challenges. Sometimes you try 8-bit and it will just destroy the accuracy for you. But then with experimentations, we learn with time that sometimes you can do the whole thing 8-bit, just that layer. If you keep it in 16-bit, it will already recover all that accuracy that we had before the quantization. So Quark introduced this mixed precision feature in which you can, through different granularities, quantize different blocks with different precisions. So if you look in this diagram, on the leftmost, we have what we call the element-wise quantization, in which, on this particular example, we are doing weights and bias in int 8, those red blocks, while the activations are preserved into int 16 across all layers, but just the terms of weight, bias, and activation. In the middle graph, we are doing a element-wise or a layer-wise quantization, in which we can say, I want like the first and last layer to be quantized in 8 bits. Everything in the middle should remain in 16-bit. Or you can be like laser focused and saying, I want this or that tensor to be 16-bit. Everything else goes to int 16. So with this kind of granularity, what we expect is that you can strike like a balance between accuracy and memory usage, or even computational time on your process. Lastly, when I showed in the first diagram that box number 5, advanced algorithms, those are, well, algorithms that act exactly doing that quantization step. And they are usually focused on a particular step of the quantization that seeks an improvement. One of them is called 8-around. I think it was proposed by the Qualcomm friends, if I'm not mistaken. And basically what it tries to do is it tries to find the optimal rounding for weights. So it will not change the 0 point, it will not change the scale, it just dynamically changes how we are going to round those weights. With this approach, we can usually recover some accuracy. Another algorithm that is similar in this sense is the AdaQuant, in which instead of using like a single set of quantization parameters throughout the model, we basically analyze statistics of those layers, and then we change those quantizations parameters according for each of those layers. So by applying that, we also see even a better recovery. Look into this example. This is a mobile app V2. that does a per tensor quantization on an int8 for both weights and activations. This model in special performs really bad with quantization. So it goes from the 85% on the full precision to 5% after quantization. But when we use 8-around, it goes up to 65%. This is 11 times an improvement just by using this algorithm. By using 8-quant, it jumps to 75%, which is 13 times more. So, and Quark supports other kinds of algorithms, which usually you can combine with each other, maybe even using that auto search feature to see which combinations yields better results, and you can recover even better the accuracy from those quantized models. So that's all that I had for the ONNX flow. I'll now pass the word to Bowen.
All right. Is give a 5-minute break. Just a 5-minute break. We had quite a few sessions, and we have 3 more coming up. So just a 5-minute break. We can start off in 2:05. Does that sound good? Okay. Sorry. We'll just take a 5-minute break before we begin. Or are you part of the NVIDIA session? Oh, I'm so sorry for that.
No worries. Thanks, Thiago. So far we've been seeing a lot of the ONNX to ONNX case where the source model is ONNX, and I'll be touching upon a few cases where the source model is in PyTorch. So we'll start with a case of one of our deployment workflow for large language models, where for Ryzen AI PC, where we quantize the model through Quark Torch and deploy through ONNX Runtime GenAI. So I think, a lot of the colleagues have already mentioned a lot of the algorithms here, and as well as the different quantization flows, either post-training quantization, PTQ, or QAT quantization aware training, or pruning. All can be configured through the Quark unified quantization config class. And once you have the quantized model, we serialize the model to a Hugging Face Quark format checkpoint. Now, this is actually key because this is the key format that we allow streamlining our Quark quantized model to various deployment backends. And in this case, we streamlined it through the GenAI model builder, which kind of takes in the Quark quantized model and then produce the quantized ONNX model. And for that matter, we're also looking forward to the new Torch ONNX exporter with Dynamo mode, as well as the adoption of the ONNX IR. So once we have the ONNX model, and we'll just go with deployments with the ONNX Runtime GenAI framework. And one of this case is one of our successful deployment workflow for the DeepSeek distilled models. There's a link on the blog post. You can look at it for more information. This part, we deploy it on the Ryzen AI PC, and this deployment flow is actually a hybrid flow, which it utilizes all the CPU, NPU, and iGPU for utilize their strengths for the different phases of the computation for the LLM inferencing during both prefill and decoding. And so Quark, in this case, is utilized to produce the model for production and to satisfy the unique kind of challenges and unique characteristics required for this type of deployment. Okay, so coming back to the overall overview of the stack of the Quark tool, I think Thiago mentioned a lot of here, so I will be repeating a lot of algorithm support and a lot of different quantization flow support. I do want to mention for the previous flow that I discussed here, it is the so-called eager mode, which simply put, it's taking a Torch model and then do very simple kind of layer and operator-wise swap out so that we can quantize the model how we want. And we also support a graph mode, which enables like even finer grained control over like, the part of the model that you want to quantize, or like the, the sub patterns or patterns of the graph that you want to like control. This is also, this is also like one of the mode that is supported in Quark TorchFlow, and it is kind of supported via the PyTorch to Torch export and FX graph kind of feature and infrastructure. And this is fully compatible with Torch export, so you can like export and deploy your quantized model through ONNX and the ONNX ecosystem. So as a user, you may say like, yeah, all these are great, right? These are a lot of algorithms, a lot of data types, a lot of flows. Like, how do I really like know which one to use or what to pick? Scan and find out, I guess. So I think, yeah, Sago has touched upon like one of the approach we have adopted is like the auto search, is try to figure out like this through the algorithm. And I think alongside that, as we are like, internally working to provide like the all kinds of like the model deployment and bringing model to production, we have accumulated a lot of these like best practices and experience throughout this workflow. And this basically gives you like on high level a nice flowchart, including some of the insights as like what kind of decision to make when like say you're starting from an initial kind of set of configurations, and what kind of observations that you're seeing, and what kind of like results that you're getting, and then how to really decide on like what algorithms to pick next, or what kind of adjustment to make to the model. Yeah, this is like, we put it as like a tutorial and a blog post so that like people can, it's really is about like a best practice of how to use Quark as a tool. And speaking of observations, we also support like some of the lower level kind of debugging functions and features while using Quark. So there are a couple of like environment variables that we created you can set to allow Quark to kind of emit and generate a lot of these intermediate data and information about to help you really understand deeper about your model, and like what kind of quantization errors or what kind of like observations that you're seeing for the different configurations you're setting. So for example, you can with one of the excuse me, with one of the flags, you can now plot all these kind of different tensor value distributions throughout the quantization. So you can take a look at like how what's the distribution of, for example, your weight tensors, and that gives you an insight like what kind of layers, which layers, and what kind of algorithms that might be helpful for overall minimizing the quantization errors, and overall like improving the model quality. And speaking of like errors, you can also plot like the quantization error for all the layers and all the operators that you have been quantized through the different configs, and then have a really insight like what is the most affecting layers in that sense. Yeah. So overall, just to touch upon again, like Quark has seen like very wide adoption, and throughout our unified format, we have deployed to various various backends and various hardwares, and we are fully open source on GitHub. So guys, if you're like, if you find this interesting, feel free to give it a try. And you can find us on GitHub, so feel free to leave us like messages and chat discussion there.